Welcome back. So today we take a look at different types of tests that can be used to figure out whether a series converges or diverges. Now, we kind of looked at that a little bit in the previous section when we took a look at partial sums and a sequence of partial sums. So we had a series that looked something like this. The sum from, let's say, n equals 1 to infinity of 1/2 to the n. And we could look at this series as 1/2 to the first plus 1/2 to the second plus 1/2 to the third, plus 1/2 to the fourth, and so forth. And then this was our series, and we took a look at each of the partial sums that went with that series. So the first partial sum was 1/2. The next partial sum was 1/2 plus 1/4, which was 3/4. The next partial sum was 1/2 plus 1/4 plus 1/8, which was 7/8. The next partial sum was 1/2 plus 1/4 plus 1/8 plus 1/16, which was 15/16. And so we looked at what we call the sequence of partial sums, and we look to see whether the nth partial sum approaches a value or not. So in this case, if we take the limit as n approaches infinity of the nth partial sum, it looks like we're heading towards 1, right? 1/2, 3/4, 7/8, 15/16. If you wanted to turn that into decimals, you could, and you could see that we were heading towards 1. What if we tried something else? What if we looked at the sum from n equals 1 to infinity of 1 over n? Now, that's not a terrible sequence or a terrible series, right? We start with 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and it looks like the numbers are getting smaller and smaller, which individually they are. But now take a look at the partial sums. The first partial sum is 1. The next partial sum is 1 plus 1/2. I'm going to write these as decimals because I think it's a little bit easier to see. But 1 plus 1/2 will give you 1.5. Then 1 plus 1/2 plus 1/3 will give you 1.5 plus 1/3 will give you 1.83. And now if you take that and add 1/4 to it, you'll get 2.08. Okay. Now take that and add 1/5, you'll get 2.28. So this is getting bigger. It's not getting wildly bigger, but it's getting bigger, and it doesn't seem to approach a limit. So because the partial sums don't approach a limit, we say that this series diverges. Even though it's not doing anything crazy, right? It's not going one of these things of 2 plus 4 plus 8 plus 16. Still, those partial sums don't approach a limit, so this whole thing diverges. This is actually a pretty important series. We have a name for it. We call it the harmonic series. And you're going to see this come up quite a few times before we're done with this chapter. So this harmonic series diverges, and the first way that I'm going to look to see whether it diverges or not is to look at that sequence of partial sums, and there's that sequence of partial sums, 1, 1.5, 1.83, 2.08. Not doing anything wild, but also not approaching a constant. All right, what's another way that I could look to see whether or not this series diverges? All right, let's take a look at this one. Suppose I looked at the series that started from k equals 1 to infinity of this particular series here. I've got 2 times 3/5 to the k plus 3 times 4/5 to the k. So this is one gigantic series, and I'd like to evaluate whether this thing converges or diverges. All right, well, it turns out that I can take these series and actually separate them into 2 different series and evaluate each of them separately. So let's look at the sum from k equals 1 to infinity of 2 times 3/5 to the k. And then I'll add to that the sum from k equals 1 to infinity of 3 times 4/5 to the k. Now you notice something about both of these series. Both of these series are geometric series. And they're both geometric series with a ratio less than 1, right? So this one, the ratio is 4/5. This one, the ratio is 3/5. Both of those series have a ratio less than 1. So therefore, I know that they're both going to converge. If I can figure out separately what each one converges to, then all I have to do is add them together, and I'll figure out what the entire original series converges to. So let's look at the a over 1 minus r, right? If it's a geometric series with a ratio less than 1, then it converges to a over 1 minus r. All right, this first one here The first term, if I put a 1 in for k, I get 2 times 3/5, which is 6/5, and my ratio is 3/5. So I've got my a and I got my r. Let's come over here and do this. The first one, 3 times 4 is 12, so my first term is 12/5, and the ratio is 4/5. All right, for each of these, I'm going to calculate my a over 1 minus r. So my a is 6/5, so I've got a 6/5 over 1 minus 3/5. That will give me 6/5 over 2/5, right? 1 is 5/5, so 5 minus 3 is 2. 6/5 over 2/5 is 3. All right, come over here and do the other one. We said my a value was 12/5. So I've got 12/5 over 1 minus 4/5. So a over 1 minus r will give me 12/5 over 1/5, which is just 12. Okay, so now if I add these two numbers together, I add the 3 over here and the 12 over there. The sum of that series is 15. All right. There are other ways to figure out whether things converge or diverge too. Let's take a look at one more, and then we'll start looking at our tests. Sometimes you got to think outside the box a little bit on these things. So let's try one, make us think a little bit. Suppose I looked at the sum from k equals 0 to infinity of 2 minus 3 to the k over 6 to the k. So the first thing you might do when you're not quite sure is to write out a few terms and see what those partial series are doing. So if I started out, for example, with k equals 0, I'll get 2 minus 3 to the 0 power is 1, and 6 to the 0 power is also 1. So that gives me 2 minus 1, which is 1. Let's skip the intermediate step and just go right to 1. Okay. What happens if I do a k equals 1? This will give me 2 minus 3 over 6. 2 minus 3 is negative 1, so I get negative 1/6. All right. How about k equals 2? I'll end up with 2 minus 9. 6 squared is 36, so this gives me a negative 7 over 36. And I got space on the screen, so I'll do one more. K equals 3. I do 2 minus 3 to the third is 27. And then 6 to the third is 216. So this gives me a negative 25 over 216. All right, so those are the individual terms. If I want the partial sums, I could do 1 minus a 6 is 5/6. And then if I do that minus 7 over 36, I'm going to end up with something that's a little bit smaller. But this thing just seems to be decreasing, but I don't know what it's decreasing to, right? So if I have 5/6, that's going to give me 25 over 36. Let's see. Come over on the side and do this. So I've got a 5 times 6 is 30. 30 over 36 minus 7 over 36 will give me a 23 out of 36. So I don't see where this is going exactly. I can see it's decreasing, and I can see it might be heading somewhere, but where exactly, I'm not sure. Let's try looking at this a little bit differently. Take that original series and break it into two pieces. So I'm going to write this as the sum of all the 2 over 6 to the k minus 3 to the k over 6 to the k. So I'm taking my original series and just breaking it apart into two fractions, making the common denominator separate now. All right, is there anything that will help me to do this? Let's take a look at that first one. For that first one, I can rewrite this as 2 times the sum of 1 over 6 to the k. Well, isn't that the same thing as 2 times the sum of 1 over 6 to the k? This second one over here actually simplifies pretty nicely. That 3 over 6 I can pull on the inside, put the k on the outside, and now that becomes the sum of 1/2 to the k. So now I've reduced these down to two geometric series, and I can figure out pretty easily how they converge. Both of these started at k equals 0. That was my original one, to infinity. Sum from k equals 0 to infinity. And so the first term here, if I leave it with just what's inside the sum, is a 1, and the ratio is 1/6. So 1 over 5/6 will give me 6/5. Multiply that 6/5 by 2, and that first piece sums to 12/5. The second one, the 1/2 to the k, if I start with k equals 0, my first term is 1, constant ratio is 1/2, so I get 1 over 1/2, which is 2. There was originally a minus sign in between them, so let's not forget the minus sign. 2 is the same thing as 10/5. I get 2/5. So that's what it converges to. It converges to 2/5. Now, if I went back to my original set of values up here, then was this originally heading towards 2/5? Yeah, but it's going to take a while to get there, right? That 23 over 36 is roughly 2/3. So I got a 1, I got a 0.83, 2/3 is about 0.67. It's going to take me a lot of terms until I get down to 0.4. So having some sort of a formula or way to evaluate this is helpful. It would also be helpful if I had some tests that I could use for series in general. So let's scroll down here a little bit and start looking at the different types of tests that we have as options. The first test we've already done, right? And so the first test, I'm simply going to remind you of what you can do with a geometric series. If the series is a geometric series, then simple test, if the absolute value of r is less than 1, it converges. If the absolute value of r is greater than 1, it diverges. And if you can use that geometric series test, then that's a real easy one to use. Try that one first. All right, not everything in the world, though, is a geometric series, so there must be other options. When you do these series tests, a lot of these different problems can be done using multiple tests. Try to pick whichever one is the easiest test to use first, right? So don't go for the hardest one. Go for the easiest one first. The next one has two names. I think the textbook calls it the divergence test. I've also seen it called the nth term test. Now, here's the deal. The nth term test only works for divergence, right? So only works for divergence. So you can use this test to show that a series diverges, but you can't use it to show that a series converges. And the nice thing about the divergence test is it's easy. If you have a series, the sum of all the a sub n's, if the limit of the nth term, as n approaches infinity, is not 0, the series diverges. But the converse is not true. If the limit does equal 0, does not mean that it converges, right? So again, my warning, just because the limit of the nth term equals 0 does not mean convergence. And so we'll take a look at a couple of quick examples here. Suppose I look at the sum from n equals 1 to infinity of 5n plus 2 over n. And I want to know, does this series converge? Well, I had said before the easiest thing to do would look at it as a geometric series, but this is not a geometric series, and so we're going to have to use some other test. The only other one we know right now is the nth term test, so let's try it. Let's take the limit as n approaches infinity of 5n plus 2 over n. Now you could say, all right, so I'm going to get infinity over infinity, so L'Hopital it. I take the derivative of the top and I'll get 5. Take the derivative of the bottom, I get 1. And so the limit is 5. What does that mean? That means that the limit as n approaches infinity is not 0. Therefore, this series diverges. So you might want to start making yourself a list of all the different tests and also what those tests mean. So in this case, the limit of the nth term is not 0, therefore it diverges, and we're done. All right, let's take a look at another case. So let's look at the sum from n equals 1 to infinity of 1 over n. Now, we've seen this one before, but let's take a look at it now using the nth term test. We said we're going to take a look at the limit of the nth term as n approaches infinity. So let's look at the limit as n approaches infinity of the a sub n's, which is 1 over n, and we get 0. Now, the nth term test said that if the limit as n approaches infinity of a sub n was not 0, it diverges, but it doesn't say what we do if it is equal to 0. Well, if it's equal to 0, that doesn't mean that it converges. So equal to 0 does not imply convergence. And so we run into the first case where the test is inconclusive. And that will happen sometimes. We'll run through a test and we'll know what happens in one case but not the other, and this is one of them. So here we come up with something that is equal to 0, but that's not what the test says. The test says what to do if it's not equal to 0. And so in that case, we say the test is inconclusive. Again, here's the harmonic series, and this is a little warning in that the harmonic series, it turns out, actually does diverge. So even though the individual terms tend towards 0, is not enough because we're actually looking at the sum of those terms, and the sum of those terms does not head towards 0. All right, so that's part 1 of series tests. Next video, we'll take a look at the integral test and the p-series test and a couple of other tests that we can use.